Hello, everybody. Welcome back to Simply ICS Cyber. This is actually the final episode of Season 1. I'm Don C. Weber, the cybersecurity guy.
And I'm Tom Van Norman, the ICS guy. And today we have Ginger Wright and Michelle Farrell from Idaho National Labs. Ginger, you want to introduce yourself?
Sure. My name is Ginger Wright, and I'm really glad to be here today. Thank you for inviting me. I'm a program manager for the Idaho National Laboratory. My current focus is cyber-informed engineering, and we'll talk a lot about what that means later in our conversation.
Thank you, Ginger. And Michelle?
Hi, I'm Michelle Farrell, and I work for our Idaho National Lab as well, supporting national security communications. So support a lot of what Ginger is going to talk to us about with the CIE program, which happens to be a program sponsored by the Department of Energy, which is a federal agency that the Idaho National Lab is funded and supported by. And we are one of the 17 national labs throughout the DOE system. INL probably more well known for their leading in the nuclear energy program space, but our operational technology and cybersecurity for critical infrastructure systems is very well known for our expertise. So I'll kick it off to back to you, Tom or Don.
Michelle, hey, thanks for that quick introduction. I just have a quick question about the national labs. I'm kind of familiar with Idaho National Labs. I'm not really familiar with like Sandia. I think it's Pacific Northwest National Labs and so forth. Can you just really quickly, what is the difference between all of the different labs within the Department of Energy?
Yeah, so all the national labs are kind of similar in their mission space, but some probably lead with more expertise and program funding for the different areas of the Department of Energy and their different mission area spaces. So Sandia probably leads more with nuclear armament and defense systems for a different sector of energy's programs. So that's why when I say ours is a lead nuclear area, the Office of Nuclear Energy within DOE focuses, probably leads more in that space with Idaho. Oak Ridge, might be more of a science lab. So they have different specialties and probably where they might lean more in with funding from DOE in certain areas.
So different types of science. So if you wanted a job there, it's basically different types of science or electrical
science
engineering.
Research. We always like to say the national labs are set up to do the things other people shouldn't and don't want to do. So, those are the areas where we can push those boundaries and do things that might not be advantageous for the private sector to do for security reasons or funding reasons. So how that pie slices changes, amongst the labs with different shifts in administration's policy, a variety of things. And Ginger could add into that too, because she's familiar as well with many of the other labs partnering with them.
As Michelle indicated, each of the labs has a different character. One of the things that I like about Idaho National Laboratory is that we have a focus on engineering that complements our nuclear approach. And we are an applied energy laboratory. We are the only energy laboratory that is a nuclear energy laboratory. We also use a lot of applied engineering to validate the science that is developed, that it will actually work in practice. And so if you ever go to our site, there are nuclear reactors where we are actually putting the fuel in, we're testing the operations are going to work as expected, and even testing those systems to failure so that by the time they get to the commercial industry, the different failure modes are well understood and mitigated. Our population is a good mix of PhDs and pickup trucks.
Interesting.
I haven't used that one. I like that one.
Well, thank you for the overview of the national labs. I didn't realize there are 17 of them. I know there's a lot of them. They all do different things, which is pretty cool. So today we're going to talk about cyber-informed engineering, or CIE. Ginger, I know this has been your thing for quite some time now, and I know personally I'm on a couple of the working groups and a big fan of it. Can you explain to us what CIE is, why it was created and funded, and what you're trying to do?
Sure. So cyber-informed engineering is an attempt to bring the engineer back into the conversation about industrial control systems cybersecurity. Often when we think about the systems that industrial control systems control, these are physical systems that have actual functional purposes. They take things that have matter or that have mass and they move them from place to place. They heat them, they change the character of them, they send them out, they pour them. This is physical activity. And when we think about the impacts that a cyber adversary could have on those systems, where we traditionally think about information technology, we think about protecting the data. We don't want anybody to take data away. We don't want anybody to change data. We don't want anybody to have unauthorized access to it. The challenge with protecting industrial control systems is, yes, we want to protect that data, but we also have to make sure these systems are safe, they function reliably, and that the product that comes out of them, whether it's energy or clean water, is what we expect it to be. And so that magnifies the responsibility for the cybersecurity tools. When we just talk to people who are specialists in protecting data, we may miss avenues to protect the system that an engineer could bring in. And cyber-informed engineering is the opportunity to marry up both of those perspectives, the engineering perspective and the data perspective, so that we're protecting the system itself and the data that helps to control it.
Yeah, when I think about some of the responses that I initially got when I was doing cybersecurity risk assessments within OT environment, and fast forward 15 years, I'm still hearing the same thing. What I mean by this is that we will have some cybersecurity assessors, people that are going in and doing a security assessments or penetration tests saying, well, I have access to this, or I can turn off that. And then ultimately an operator just says, so go ahead and change that, make that change. It doesn't really, well, it might affect something. And obviously we want to be in control of things. Not everything has the cascading effects that we're used to on the corporate side. And so when I was doing some of the CIE training, I was fortunate enough to go out up to Boise to do some of that training. I really kind of learned about the fact that the engineers are looking at it like, where does the energy flow? What are the bottle gaps? What are what's the supply chain issues? And so thinking about the cybersecurity inputs and outputs that will affect those things that they need to run, that's kind of something that came out to me. Yeah, can you expand on that a little bit, Ginger?
Sure. So I'll tell a story if you'd like. Imagine that we have a pressure vessel, and in that pressure vessel, we are cooking up a chemical, and we have to get it to a certain temperature and under a certain pressure for it to change into the result that we want. If I think about that pressure vessel from a safety perspective, I probably somewhere put a pressure relief valve in that vessel. And I did that in case someone operating the system accidentally got things out of control, or in case one of my safety systems failed and that tank began to heat up either more or experience more pressure than it was designed to. And without that pressure relief valve, eventually the tank would go boom, and that would be a very, very bad day. With the pressure relief valve, the tank goes out the relief valve, and that's a bad day. That's a messy cleanup, but the humans that surround it, the environment, they all stay safe. So what cyber-informed engineering allows you to do is, when I think about a cyber attack, again, there are definitely data attacks. We should protect that avenue. But what if an adversary is really trying to disrupt the function of the system and cause that tank to go kaboom? Well, we already have these ideas that we've used for safety engineering. If we can bring those in to protect against the consequence of a cyber attack, now, even if all my digital technology fails and the adversary has complete control, there's a limit to what they can do on my system that will hurt me. They might be able to create a bad day and I might have a cleanup to do, but it will take me away from the worst possible day, which would be that tank exploding.
Ginger, what industries have embraced this?
So the energy industry is embracing this. We have asset owners that are using cyber-informed engineering to control the blast radius, and that's their language of a cyber attack. They like having the digital protections that they have, but they like using cyber-informed engineering to put an additional control in. Equally, the water industry has been a very strong proponent. We've had in Idaho, our Department of Environmental Quality recently did a funding call for clean water and wastewater projects that would actually take place. They would be built, they would be enacted in next fiscal year in 2026. But the proposal call was just issued. In that call, the Idaho Department of Environmental Quality gave 20 extra points to anyone who proposed a project that incorporated cyber-informed engineering. And then that meant we had a lot of engineers coming to us looking for training, looking for advice, looking for tools. How do we incorporate that into systems? The reason that Idaho did that was to ensure that as new digital products are put online in our water systems, we're providing the best cybersecurity, thinking about it early in the design life cycle before we build that system, put all the technology in, and then realize we have extra needs to protect it.
I mean, what you just said right there, what's like design for new. I mean, so is this something that can be applied to brownfields, or is it just a greenfield kind of thing?
So I don't know if everyone is familiar with that terminology. Often in critical infrastructure, we refer to greenfield projects as the chance to walk out in and imagine a green field with the grass mown, and we can just build whatever we want there. And cyber-informed engineering is excellent in a greenfield application because we can design the cybersecurity in. When we think about the factory before we build it, or the water system before we put the UV thing in that's going to clean up whatever goes through from a waste perspective, we have a chance to say, what digital technology is being used? How can we ensure that an adversary, if they got a hold of it in the worst way, is limited in what they could do? Brownfield projects, on the other hand, mean that we come in with the factory's already there, the process is already there, all of the equipment is there, and we're modifying it or changing it to add extra security. So cyber-informed engineering works absolutely best in a greenfield environment because we can make all of the security decisions at the beginning and design it in. However, we illustrate often a brownfield environment where we're changing something that already exists and adding protections in, and you can do it for specific applications. So your approach might be less holistic, you might be more targeted in what you do, but the thinking works in both a brownfield and a greenfield environment.
So, Ginger, before doing all this stuff with Don and whatnot, I worked a lot in process control, in different utilities, process control, chemical environments, biotech, things like that. And I'm used to going through risk assessments and, working with engineers, and, they put the rupture discs in, they put the relief valves, they size the pipe the right size, and, things like that. Not for a cyber event, but to make the process work. If you need to pipe that pipe, or if you need a vessel that needs 100 gallons a minute of flow, you can't put a 1/4-inch pipe. Doesn't work. So, coming from that world where the engineers are all tuned into making the process work, how reluctant or how reluctant are they to accept the cyber end of things when they're already putting in rupture discs and right size piping and things like that? Do you get pushback at all?
Some, like many things, your approach depends on, or the acceptance of what you're saying depends on the approach you take. So often explaining to these process engineers that all of this digital technology that has quickly crept into the engineering and the critical infrastructure landscape, that these are general purpose computers. And even though this device or this system may say on it that it's an electron microscope, or it's a pressure, or that it's a protective relay, behind it is a computer. And that computer can be reprogrammed to do things that are beyond what that system was designed to do. Once the engineers understand that, and that those dastardly digital folks have created an environment that doesn't work like an engineer expects it to, they then quickly come to understand using cyber-informed engineering basically allows them to make these digital systems behave like an engineer expects, that something is designed for a purpose and it can only execute according to that purpose, and that the states that it can be in are all documented and known, because that's what engineers really, really like. So what we try to do when we talk about cyber-informed engineering to process control engineers is help them understand how they can control what the digital technology is doing by applying these tools, and the need for them to really talk to their cybersecurity person about what is the worst thing that could happen. If I have this protective relay, how might an adversary make that behave in a way that my process doesn't account for, or that I wouldn't be expecting?
Now, is this different than a cybersecurity assessment? I mean, I know that it is different. I mean, I know that the questions are different. The goals are slightly different, while you're taking into account a lot of different technologies and how they're interacting together. So this would be something separate than a vulnerability assessment, pen test, security assessment. Is that accurate, or is there more context around that?
That is accurate. I'd love to provide a little more context. The key difference is when I perform a cybersecurity assessment, I'm typically evaluating a cybersecurity program that was designed to put really deep obstacles in the way of an adversary who might be traversing a digital pathway on the way to accomplishing an effect. And that's the whole purpose of a cybersecurity program, is to make it the highest and the worst obstacle course possible, to limit the possibility that an adversary actually gets to that destination and can do whatever the thing is that they want to do. With cyber-informed engineering, I'm not saying take all your cybersecurity out. Please do not read that into what I'm about to say. But we focus first on what is that consequence, and can I use engineering? And the neat thing about a lot of the protections that Tom's team would come up with is that these things may not be digital. They may not be things that the traditional adversary could even have access to, like that pressure relief valve or that burst disk. There's no way for the adversary to get on a keyboard and mess that up. So that's there. The adversary can't see it. They can't touch it. It's a protection that will always be there. And then once we think about that around this critical function, then we can add the obstacle course to put in their way as well. If this is a really impactful consequence, something that would affect the safety of people, the reliability of a critical process, or the potential for environmental damage, it makes sense to have a protection in-depth strategy that includes both engineering and physical protections and all those cybersecurity protections.
Very interesting. There's certainly a lot that goes into the program. What are some obstacles for deploying it? We talk about greenfield, brownfield, things like that. Hey, how do you get people bought in? How do you start this? Where can we go for information? What can we do to start it?
So great questions. The first and biggest obstacle is that this is a completely crazy idea. Why in the world would we protect digital equipment with physical things? If you look, and Don, you're familiar with all of the methodologies for doing cybersecurity, there's not one of them, even on the back page in the bottom of an appendix, that says, hey, why don't you call your engineer and see if there's anything they could do to make this attack effect impossible. There's no methodology that suggests that. So the first obstacle is getting people to understand, again, for engineered systems, for critical infrastructure, the link between the cybersecurity, the digital protections that we're familiar with, and the physical world that's being impacted. What we're trying to do to change that is to bring cyber-informed engineering into engineering education. So the next process control engineer that's graduated understands how that digital equipment can not be what they expect it to be, and the need to use their engineering understanding to put limits around it. The second obstacle is for a person who's adopting this to be able to show, I was absolutely mature in my cybersecurity strategy. I not only did the checklist things that the various processes that we endorse suggest that I should, but I also put these physical limitations in place. So we're working with standards bodies to try to add these ideas to standards so that we can show that interplay between the digital world and the physical world. And the last obstacle is that this takes bringing people together. And the two of you epitomize the groups that we have to bring together. It takes bringing your ICS person with your cybersecurity person and having them really think about the physical effects of an attack, the protections that could be put in place from a digital perspective, and how engineering can meet the gap.
I mean, when I think about vulnerability assessments, penetration tests, we usually only have a specific amount of time, 3 days, maybe 5 days to look at a specifically scoped target. And when I first started hearing about this from Tom and Tim Conway, they were talking about how long this process can be. What is the experience thus far now that we've seen actual implementation? Obviously, we've got to discuss a lot of things, a lot of complexity. The scope might be a little bit larger than a general security assessment. So how long could should somebody expect this type of effort to happen? How do they need to staff it?
So I'm going to give you a very typical national lab answer, and that is, it depends. But let me clarify that. So with cyber-informed engineering, you really have a choose your own adventure opportunity. The classes that you took were focused on consequence-driven cyber-informed engineering. And that is for processes that have national impact. If something goes wrong, we will not only feel it as a business or as a region, but we will feel it as a nation. And that process is very in-depth and takes a great deal of knowledge to execute. It's a good one. But any organization can take the parts of cyber-informed engineering, which is sort of the larger philosophy, and pick the questions or the aspects that most matter to them. So I'm going to hold up. We have an implementation guide that we've created, and I'm happy to give you a link to that. It has a series of questions, and the number of questions in the book, over 1,000, it can be overwhelming. But the idea behind this guide is pick a few of the questions. Start with the consequence evaluation piece, pick a few other questions, pick areas where you'd like to build some strength anyway, and start. And then if that pays off, as that pays off, go a little bit deeper. We've also designed a set of tools. As we interacted with one of our asset owner partners, this was a statewide cooperative, and they said, we really love the 1,000 questions, but can you give us a tool that would let us get to the 80%? Because if we knew we could quickly get to 80%, we would have some breathing room to think about what to do next. So we've created a tool called CIE MAT, that is the CIE microgrid analysis tool. We've also created one called CIE BAT, that is the CIE battery energy storage system analysis tool, that will let you quickly get to what are those things that most matter, what do I need to put in place to strengthen my security approach, and how can I quickly do that?
Ginger, this podcast is heard by people that are not familiar with ICS or OT and may have never been on a plant floor. Can you give us some examples of an outcome from CIE? Would it be to install a firewall? Would it be to install segmentation, or would it be to install a different pipe or a rupture disc or a valve or something? What is the outcome?
Well, one outcome could be talking about whether the firewall, the rupture disk, or a combination of them all is the most important. The first thing we want to ensure is that when you ask the cybersecurity guy, and Don, I'm looking at you, what's the worst thing that could happen if an adversary got in this system and absolutely went ham, I'll quote my daughter, and did everything that they could possibly do? Often the cybersecurity person says, you know, if it's an ICS system, I don't really know what that worst possibility is. I know what the institution values, and so I can say we don't want these things to happen, but specifically, I don't know. So by pulling these questions, by pulling these experts together, one outcome we hope for is that both cybersecurity and engineering get informed about the things the system must always do and can't ever do. And that then, as they design protections, they're aligned on how they fulfill those responsibilities. Whether the engineer says, okay, a rupture disk is the right answer, or the cybersecurity person says, you know, I'm not comfortable with just a rupture disk. What if we do some network segmentation as well? At least you're thinking about a consequence that that system could impact.
So
Yeah. And I think that's an excellent example that we need people from the cybersecurity side to understand, is that the remediations to what I don't like to call them vulnerabilities, because vulnerabilities are in products. I like to call them implementation issues within these environments. The solutions, the mitigations for those could be some type of countermeasure, some type of configuration change, or it could be some type of physical thing, just being prepared to disconnect, or actually, why is that system even online? Can we just get it off the network? Those types of things. I think it's important for people to understand, especially this crowd, if you're moving into
to
that
build
area.
on that,
Mm-hmm.
I had one assessment where the answer was a contract. So let me set this up for you. We had a giant computer system that's purpose was logistics for a very serious national mission. And in this case, this was cloud before cloud was cool. So imagine a warehouse with lots and lots of gleaming computers, and there wasn't a single computer that was most important. The data was scattered across all of them. In this case, they had a water-fed heating, ventilation, and air conditioning system. And as you might imagine, it had a water tower, and people had spent a lot more time securing the warehouse than they had the water tower. And no one realized, oh, if the water tower goes out, well, then the heating, ventilation, and air conditioning system goes out, and there go my gleaming computers. So in this case, one of the potential cybersecurity things to do would be to have a contract ready with a construction company that on an order, they could roll trucks of water, so that if that water tower was taken out, as is a possibility, we have water to feed our air conditioning system so that we're independent of the water supply to continue. This is the kind of thinking that cyber-informed engineering allows you to get through, really focused on resilience as well as defense.
That's awesome.
That's definitely a much needed program, in my opinion. So the recap on that, after you do your run through the assessment there, it's up to the people that are doing the assessment to decide if they need a network segmentation or a firewall or rupture disk or a contract. The program's not going, the assessment's not going to say you need this. It's going to make me talk to Don, and between Don and I, we're going to come up with the risks associated with that, and we're going to figure out the mitigating tools.
Yes. Now we've developed some documentation to help. We have a product that West Yost helped us to create that looks at, if depending upon your risk mitigation priorities. If you're a Krispy Kreme rather than a nuclear plant, you both have mission critical ICS, but the money and the time that you need to spend on protecting that critical mission is clearly different. So it helps you walk through how to prioritize what you do. One of the things out of that document that I'd love to recommend here is that you actually do an exercise of a day without automation. What would happen if an adversary made all of my automation untrustworthy so that I couldn't depend on it? It might not work correctly. Do I have what is needed to then resiliently operate my function? And if I don't, where should I focus first? That's a great exercise for clarifying the priority of how you might apply these corrections or mitigations.
Awesome. Hey, Michelle, we've monopolized the conversation. And we're right at the end. Can you let us know? Do you have any final thoughts around this whole conversation about this, about the labs?
No, I think this has all been great and helpful. I think I'm hearing a little bit of saying maybe CIE is the answer to the IT/OT convergence or bringing the worlds together. Maybe I'm pushing it a little bit, but I know I've been in those conversations with Tom, and it's the ongoing conversation. But I think we have tons of tools and resources available at Idaho National Lab. Ginger's a great resource. We have a webpage that has all the tools and guides that she mentioned in this podcast. So inl.gov/CIE, please go to it and continue the conversation. We'd be happy to collaborate with anybody and join our working groups as well.
Yeah, we'll make sure we get that in the show notes. Ginger, any closing thoughts?
So we would love to have you participate in our working groups. We'd love to have you use these resources. The Department of Energy's Cybersecurity, Energy Security, and Emergency Response Organization has funded the Cyber Informed Engineering program for several years. And our goal is not to do a lot of great research in the dark, but instead to get tools out that industry, that users can apply. And if you have an idea for something that we can do that would get this idea out more quickly to the population that needs it, we would love to hear about it.
Awesome. Well, I couldn't have imagined a better group of people and a better topic to end our season on. And, I highly encourage everybody, if you're not familiar with this is definitely something that the industry is looking to. You should be informed about this if you're going to be working in cybersecurity programs within the industrial and automation arena. It's something that you should have in your toolbox. So that's my final thought. Tom, what are your final thoughts for this episode and the season, bro?
Nate, it was great having Michelle and Ginger on to talk about what national labs do, what CIE does, and Don, looking back at this whole series that we did, we had some really great podcasts with some good feedback. People within government, people within the labs, people within industry. So I highly encourage people, if you're interested, go back and look at the previous episodes.
Awesome. Well, thank you very much, everybody. We're going to end it on that. We're a little slightly over time. Ginger, Michelle, thank you once again. And Tom, thanks for doing this with me. I really appreciate it. And I'm looking forward to next season.
Thank you.
Thank you.
Here. Thank you, everyone.